Assalamualaikum and good day everyone. I am AMIRA and in this video, we from Group 4 will explain our lab reports on Experiment 5, which is Bending Moment Experiment. Our group consists of me myself, AMIRA, NASREEN AINA, DIYANAH, ALAZIM and MOHAMAD FIZRI HAZEEM. So, proceeding with the experiment, the objective for this experiment is to measure the bending moment of material.
Assalamualaikum warahmatullahi wabarakatuh. My name is Najraina and I'll be explaining about this theory of the experiment. So internal stresses and strains are created when a beam is loaded by force or couples. These stresses and strains can be determined by finding the internal forces and internal couples that act on cross-section of the beam first. In figure A below, a cantilever beam is acted upon a vertical force, P. When the beam is cut through a cross-section, for the left-hand part, in part A, the shear force Qx in the blue box and the bending moment in the red box are assumed to be positive in the directions as shown in figure B and C respectively. This positive direction is vice versa if the right-hand part in part B of the beam is considered. For vertical equilibrium of part A, there must be a shear force Qx acting as shown in figure 1b in the blue box and actually equal to the negative Ra. For vertical equilibrium of part B, the shear force Qx evidently acts as shown and has the value of P minus Rb.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is MOHAMAD ISMAIL and today I'll be explaining both the apparatus and the discussion part of experiment 5 bending moment. Okay, for the apparatus part, as you can see, there are experimental beam, spring balance, load hanger which are classified into P1, P2 and P3. And lastly, the different load that we have are 2 Newton, 5 Newton and 10 Newton. Okay, we move on to the next presenter.
Hi, my name is NOORDIN. So today I will be explaining about the procedure for the experiment 5. So in the experiment, we have two parts of procedure. So the first step in the part 1 is we need to set up the beam. So how to set up the beam, we need to refer the indicates in the slide. So after we set up the beam, a load of hanger we placed on the middle part of A, and then one on the part B and one at the joint just over the bearing pin. Then the third step is set the spring balance so both parts of the beam are aligned and record the initial reading of P1, P2 and P3 using the table 1. So the fourth step is by applying the 10 Newton weight to part B, we need to realign again the beam and change the reading of the spring balance using table 1. Then we can determine how 10 Newton weight affect the beam reading. Then using table 1, record the distance between this weight and the right hand support. Then the last one is we need to repeat the experiment with 20 Newton load and the hang over the bearing pin. So move to part 2. The first step in the part 2 is we need to install 3 load hanger as desired, which is P1, P2 and P3. We can refer to the figure below. Then align the beam and take the initial reading for the spring balance in the table 2. Then second step is we need to place weight on all 3 of hangers and realign back the beam and record the new reading for the balance. Then the last step is we need to repeat the experiment in part 2 but with the different position and load. Then record it as a new balance in table 3. Okay.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is NOORDIN binti RAHMAN and I will be discussing about the data, analysis and results of this experiment. This is the data given and measured from the experiment. And as for the results, I'll start first with table 1. On the right hand side shows the bending moment at C for the load configuration in part 1. And for the left hand side shows the table and value obtained from the calculation. Next, the table below shows the calculation of bending moment for each load given, where we can calculate by multiply the net force given from data with 150 mm. Next, this is the calculation to obtain theoretical moment at C, where we need to find value of RA first in order to get MC. From here, we can observe that the every force P1, P2 and P3, the load of 20 Newton is twice more than load 10 Newton, and it is also the same as the theoretical moment at C calculated. Next, for table 2, this is the result that we obtained from calculation. Next is the calculation to obtain bending moment and theoretical value of moment at C, where we get the bending moment of P2 is equals to 5 is 1050 Newton millimeter, and the theoretical obtained is 999 Newton millimeter. Also, for bending moment of next load obtained is 2700 and theoretical value is 2668 Newton millimeter. Lastly, for table 3, we need to calculate bending moment at different positions and load. This is the result obtained for table 3. The calculation is based on the diagram of bending moment shows. For the first bending moment of load P1 and P3, we obtain 1500 Newton millimeter, and for theoretical, we obtain 1934 Newton millimeter. As for next load of P1, P2 and P3, we obtain bending moment at 2400 Newton millimeter and 2600 Newton millimeter for theoretical value. That's all from me. Now we proceed with the next presenter.
Hi, I'm going to explain about the discussion. Okay, first of all, the question asked was, when the load was double in part 1 of experiment, did the bending moment double? Explain your answer. Okay, from the data that we calculated, for load equal to 10 Newton, the value that we obtained for P1 is 600, P2 is 1800, while P3 is 900. For load of 20 Newton, we obtain P1 equal to 1200, P2 equal to 3600, and lastly P3 equal to 1800. Okay, based on the calculation from part 1, we can conclude that when the load increased, the bending moment also increased. By doubling the stress, we can observe the bending moment will be twice the value from the first load. Besides, our answer before is also supported by the theoretical value calculated, which also shows that the bending moment doubled when the load was doubled. However, due to some random error occurred during the experiment, the data calculated slightly deviated from the theoretical value we supposed to obtain. As an example, we obtained the 600 Newton millimeter for the load of 10 Newton at P1, while the supposed theoretical value should be around 667 Newton millimeter. Then, for load of 20 Newton still at P1, we obtained the value of 1200 Newton millimeter, while the theoretical value is supposed to be 1334 Newton millimeter. However, we can observe that both values double once the load was double on both experimental and theoretical value. Okay, for the second part, we are asked to compare the average figure for each of the experiment by using the bending moments value obtained from the experimental and theoretical. Use either a ratio or percentage error. Okay, we have decided to use percentage error. The formula is modulus experimental value minus by theoretical value modulus divided by theoretical value times 100%. Okay, for the 10 Newton load, the percentage error that we obtain at P1 is equal to 10.04. Besides, for the P2, we also obtain the percentage error 10.04, the same as we obtained at P1. And for P3, the percentage error we obtain is 9.91. Okay, for the 20 Newton load, the percentage error that we obtain at P1 is still the same, 10.04. But for P2, it is slightly different. We obtain percentage error of 9.98. And lastly, for P3, it's the same as P1, still 10.04. Okay. To calculate the average percentage error for a load of 10 Newton, we take all the value of percentage error at 10 Newton, which are at P1, P2, and P3. We add all the values and divide it by 3. And the value that we obtain is equal to 9.997%. Okay, we do the same for the average percentage error for load of 20 Newton. We take all the values of the percentage error at load 20 Newton, which are at P1, P2, and P3. We add them all and divide it by 3, and we get equal to 10.02%. Okay, for the next slide, we are still finding the percentage error, but in different cases, such as you can see at table 2 is the data for bending moment at C for the load configuration in part 2, while for table 3, data for bending moment at C for the load configuration in part 2, but with different positions and load. Okay, we move on to the table 2, and as you can see, for the part of P2 equal to 5, the experimental value we get is 1050. The theoretical value we got is 999, and still by using the exact same formula as the slide before, to calculate percentage error, experimental value divided by minus by theoretical value, which is in modulus, divided by theoretical value times by 100%, and the percentage error that we get is 5.11. Okay, for the P1 is equal to P3 and P2 is equal to 5 part, we can see the experimental value that we obtain is 2700. The theoretical value is 2668, and the percentage error that we get is slightly more decreased than the first one. As you can see, there is not much different for the experimental value and the theoretical value. We get 1.20%. Okay, for table 3, the load Newton for P1 is equal to 5 and P3 is equal to 12. The experimental value that we get is 1500, while the theoretical value is 1934. Okay, by using still the same formula, the percentage error that we get is 22.44%. This is quite big actually. As you can see, the differences between 1500 of the experimental value that we get and the theoretical value is quite large. Okay, for the P1 is equal to 5 and P2 is equal to 10 and P3 is equal to 2. The experimental value that we get is 2500, while the theoretical value is 2600, and the percentage error that we obtain is 7.70%. Okay, from the table we can conclude that the average percentage error for both load 10 Newton and 20 Newton are almost the same, in which they occur due to some error. Besides, for table 2 at P2, the experimental value is close to the theoretical value. That is proven the bending moment to be true. I think that's all from me. Thank you.
While handling this experiment, there might be some possible errors that occur. First, when taking readings, parallax error might occur due to the position of eye deviate from the supposedly right position. Next, the hanger might move during the realignment of the beam. And lastly, the scale of the spring balance might be not accurate, hence affecting our readings. Having this error listed, we can take precautions by ensuring that our eye is perpendicular to the scale while taking the measurement to avoid any parallax error. Ensure all the hanger are on its right position during the realignment of the beam, and always check the spring balance has accurate scale. In conclusion, this experiment is successful as we achieve the objective of this experiment, where the value of experimental and theoretical values are almost the same, which the slight differences might come from the errors while doing the experiment. Other than that, we can conclude that the value of bending moment double as the load double. The force and perpendicular distances are directly proportional with the bending moment. As the force and perpendicular distances increase, the bending moment also increases. That's all from us. Thank you.